Hello AP, I'm going to discuss today 2.8 ionic compounds. And in 2.8, when you name ionic or molecular compounds, it's a name called nomenclature, as you see right here. So nomenclature is just another way of saying the naming rules for any type of compound. Now I'm going to first start off with ionic compounds. And remember, ionic compounds is about losing and gaining electrons. Okay? And the type of elements that do this is usually metals and nonmetals, or metals and polyatomics. And very rare can you actually have like a polyatomic and a polyatomic. Okay. Very rare also, even if I went even more specific with that, polyatomic and maybe even like a nonmetal. Okay. So as long as you have ions, and more specifically two types of ions, cations always like to lose, and anions like to gain. So cations lose electrons, anions like to gain those electrons. Okay, so as long as you have one of each, and the cation always goes first, and the anion is always listed second. Okay. So be very careful when it comes to naming that you understand the difference between, is it an atom or is it an ion? So notice with cations, if I have just listed the word or listed the symbol sodium, well, that's a sodium atom. But as soon as it loses an electron, it becomes a sodium ion. Okay? So it's not sodium no more, it lost an electron, so it's sodium ion. As you see in the periodic table down below, and you may want to pause the video to grab your periodic table to label, but everybody in group 1 has a common charge of +1, even hydrogen, and everybody in group 2 has a common charge of +2, and we'll get to the transitions in just a second. Everybody over here in 3A, +3, and then +4, and I'm not sure why some of the symbols are missing, but everybody in these groups do that. And then as soon as you get to about right here, then you start to gain electrons. Okay, now notice below this purple regions, it's not here, it's because those are metals, and metals are still losing. Okay, so these symbols that are actually shown in here, these are just common charges. So it starts to go backwards, gain 3, gain 2, gain 1, and then we will hardly ever talk about the noble gases unless we're actually drawing structures. But other than that, we aren't talking about anything with them when it comes to bonding. Now, in this periodic table, if I actually drew the staircase, and I believe your periodic table for AP does not have that staircase, okay? Anyone that touches this line is a metalloid, excluding aluminum. Now, those metalloids could actually be positive or negative, okay? So they actually could be maybe like a +3, but it could also be maybe like a negative something else. So these numbers that I listed on top of the groups, these are just common charges, but do know they can have other charges, okay? So like, for example, like 10. 10 is +4 commonly, but it also can be +2. Same thing with lead, +2 and +4. And in the transitions, they have many different charges. Many. Okay? But the ones you definitely want to know are the ones that you see here. Okay? So very easily, chromium, manganese, iron, cobalt, +2, +3 most of the time. Okay? Do know that manganese has several charges compared to a lot of these transition. I know he's got at least 7 to 10 different ones. So every time they lose an electron, what happens is they change color. The solution, the homogeneous mixture changes color. So like manganese +7 is like a purplish type of substance. But if it's like +7, it's a different color. I want to say it's about brownish. And if it was a +6, it changes a different color. So every time atoms lose electrons, they will change colors to the solution. And it's something called oxidation numbers. And you'll hear more about that in chapter 20. But common ones in here that never change are silver, zinc, and then obviously this aluminum. So remember that staircase, +1, +2, +3. Okay? And the reason why I mention that is because any elements, so here comes the next rule, any elements as in transition metals, and I'm going to put even, and under the staircase. You have to indicate in the name the charge. Okay, so it's this thing called the Roman numeral. So is it copper +1 or is it copper +2? So when you actually name it, you actually have to put the Roman numeral in the name. And the Roman numeral, what it indicates, it's the charge of the cation. So the charge of copper, or the charge of manganese, or mercury. And we'll talk about mercury. I'm going to put a little star by him because he can get a little tricky. And then polyatomics, there's only 2 of them that actually are positive. Ammonium and then hydronium. You'll see hydronium when we get to chapter 16, definitely chapter 16 and 17. And then ammonium is definitely going to pop up in those chapters when we talk about bases. But do not confuse ammonium ion with this guy, NH3. That's ammonia, so an ending of IA. That's a molecule. That's not an ion. So an ion, you physically have to see the charge on paper. Okay? So when you're looking at the positives, well, there must be a negative part about this too. And then we'll do some practice problems. So the anions, a little bit different. So notice when we put Na+1, well, that was sodium, but sodium ion. Okay? But what happens when you actually gain? So the anions are gaining electrons. And when they gain electrons, not only do they gain, but something happens to their name. And it's this IDE ending. So when you gain electrons, become those anions, those negative charge ions, you do change the ending to IDE. So I like this example that I put on here so you see the difference. Just normal chlorine on the periodic table is a chlorine atom. But those diatomics aren't chlorine no more. That's a chlorine molecule. And if you put a charge on it, then it becomes obviously chloride ion. Because of the negative, you got to change the ending. Okay? A couple polyatomics that actually do have the IDE. And I like these because all of them that actually have the IDE ending, except the peroxide one, these two, hydroxide and cyanide, they do have a -1 charge for each. Peroxide has a -2. Okay, so they're the only polyatomics that actually have an IDE ending. Okay, polyatomics are basically many atoms. Word poly means many, so many atomic ions. So many atoms with the charge. Okay, so somewhere in there they actually gained an electron. So we have a certain type of polyatomics called oxyanions. So we're talking about negative charge particles that somewhere have oxygen. That's why it's called oxyanions. So negative charge particles that contain oxygen. Okay, now how many oxygens? Well, that depends on the name. Now, we don't really go too much into this in honors and CP, but you do need to understand the difference between ATE and ITE. The one that actually has more oxygens is ATE. The one with less oxygens is ITE. Okay, so like I said, you only see 2 polyatomics with IDE endings, but the other 2 is either ATE or ITE. And here's the cool trick with it too. Nitrate and nitrite, -1, -1, they got the same charges. So that makes it even easier too. And the other thing that doesn't change either is the number of nitrogens. The only thing that changes is the number of the oxygen that's bonded to it. Okay, so ATE is more oxygens, ITE is less oxygens. Okay, and you have the same charge for those particles. A little trick with the halogens, okay, and every halogen does this. Okay, it's a cool little trick that I do. Okay, if you actually put the polyatomics for chlorine, just line them up. So chlorine with 1 oxygen, 2, 3, and 4. And notice also the charges. They're all -1. Same charge. Okay. Well, you know that the one with the more oxygens has that ending ATE. And the ones with the less oxygens have that ending ITE. So my trick is, write these first 2 the same word. Just write the same word for both of them. So chlorate, chlorate. And for the last two that have 1 or 2 oxygens, write the ITE. Okay? Now the last addition is the one that has 4 oxygens versus the one that has 1. You just have 3 or 4 little letters to add to the beginning of it. So hypo, okay, hypo meaning 1 oxygen, so hypo. And then per means 4 oxygens. You're going to see that when you see the polyatomic called permanganate. Permanganate has 4 oxygens also. So there is a reason why they call it per. Some students like to say like tetra for 4, and it's not molecular. We're not talking about molecular compounds or anything like that. Okay. You can also add hydrogens to polyatomics too. So like for example, if I have carbonate, carbonate is -2. But what if I want to keep a polyatomic but add a hydrogen? Now before you start crisscrossing and trying to make a, oops, sorry, +1. Before you try to crisscross and make like an acid, I didn't ask for that. I wanted to keep it a polyatomic. So what happens is if you add these two charges together, +1 -2, and bring the symbols together, well then what's left over is -1. And you call it hydrogen carbonate, not hydrocarbonate, hydrogen carbonate, as you see right there. But in AP, or actually not AP, but in the world, they also can name this polyatomic called bicarbonate. Okay? Same thing for phosphate. Phosphate does it also. So if I take 1 hydrogen and I put PO4, -3 is phosphate. If I add those two together, not crisscross, add them together, then I get 1 hydrogen, PO4, but now it becomes -2. So then the name is called hydrogen phosphate. And you can even call it biphosphate. Okay? But there is another polyatomic that actually has 2 hydrogens. So what if I take H+, and PO4 and just add that all up? Well, I'm not going to put HHPO4. I'm just going to add those two H's together. So I'm going to call it H and make a subscript of 2. PO4. Basic math. +1 + 1, -3. Now I got -1. So we have to actually name that 2 that's in that formula. So now we say dihydrogen. So be very careful with that prefix of di versus bi, because it can get a little tricky. Okay. Other than that, ladies and gentlemen, you have a list of polyatomics, and make sure you know those polyatomics. So let's practice on how to name. I'm going to kind of make this a little bit smaller so we can see our little periodic table that's over here. Okay. So when you're naming compounds, first thing is you need to write the charges. So sodium and chlorine, we're going to come together. I'm sorry, we're going to name it. I was kind of working backwards. So these are all ionic compounds, and just be very careful about that ending. So I got sodium, and it's not chlorine no more because it gained electrons. We now change the ending to IDE, chloride. And you never have to capitalize names, just all lowercase is fine. I have strontium, and then I have oxygen, now becomes oxide. Okay. I have aluminum, and then nitrogen becomes nitride. Okay, so I know your periodic table does not have names on it, so spelling is going to be very important. Now, just because it has a subscript, you don't have to call it dichloride. This is not molecular. We don't name how many you see, okay? But the only prefix we actually do that for with polyatomics or molecular, but not ionic. I got 2 chlorines, that's okay. I still got chloride. Okay. Over here, real quick on letter V, I have potassium. And just because I have 2 potassium, I don't call it dipotassium. And I got oxide. Not monoxide. We only use monos, dis, and tris if we were actually doing molecular compounds. Now I'm going to make this last part bigger because I have 2 elements, and both of those coppers are transition metals. Okay, so make a big note. Anytime you have transition metals, or under the staircase. There are some exceptions, okay? You need those Roman numerals, okay? So if you're transition metal or under the staircase, you need those Roman numerals. So like I said, some exceptions are silver or zinc. Don't need to put it. If you do, that's fine. But because remember, silver is always +1 and zinc's always +2. And aluminum is under the staircase. But do not put Roman 3 because he doesn't have any other charge. That's it. He's 3. Okay? So do not put Roman numerals for these ones. So I got copper and I got oxide. But notice the second one, I also have copper and I have oxide. But we got to figure out what those charges were. So it's like what I like to call working backwards. I have to, oops, sorry, not cap. I have to figure out what those Roman numerals are going to be because copper is a transition metal. So when you're doing this, we don't know what copper's charge is, but we know oxygen's. If you look at the periodic table that was right here, we know oxygen's -2. And because I know he's -2, well then I could put -2. So like I said, it's like what I like to call working backwards. We know ionic compounds have to be electrically neutral, and I don't see any subscripts in this compound. So something -2 has to be 0. So I know copper has to be +2. So oxygen's -2, copper must be +2, so I'm going to put Roman numeral 2 with that copper. Because remember, the Roman numeral is about his charge, about the cation's charge. But what if I actually have a subscript? Okay, same thing. If I have copper and I have oxygen's -2, and this has to equal 0. But I have 2 coppers, and when you do the charges have to be for one of the coppers. Okay, so something -2 has to be 0. And I know you're thinking, well, the answer is also +2. That would be if I had 1 copper. But because I have 2 coppers, I have to take that +2 and divide by 2. So 2 divided by 2, so the copper is really +1. Okay, and that should make sense, ladies and gentlemen, because if you had copper +1, oxygen -2, crisscross. There's where that 2 comes from. So I like to call it sometimes the reverse crisscross, but it doesn't always work. Okay, so I can't make it a law out there in the world, but I like to call it working backwards instead. So copper, I'm going to put Roman numeral 1. Okay, the last couple of examples is when you actually have to write the formula. So when you write the formula, it's always good to show your work. So you have a periodic table, you have a polyatomic chart, okay? So let's go through them. Try it yourself first, and then push play, and then check your answers. So ammonium, NH4, is a polyatomic, and nitrate, ATE, polyatomic, NO3-. They need to be electrically neutral, +1, -1, so then we put them together. So this is what I like to call the before and after. Okay, so before is the charges, after is when it forms that compound. Copper, Roman numeral 2, so charge of +2, and then bromide, -1, according to the periodic table. Doesn't equal neutral, so I'm going to crisscross those charges. And remember, when you crisscross the charges, you're just crisscrossing the numbers. So copper, and then bromide, and I'm going to put the 2 right there as a subscript. Copper +1, and then bromide. Now this one is electrically neutral, so we're just going to put them together. Okay. Zinc, hydrogen sulfate. So zinc on the periodic table is +2. Hydrogen sulfate is a polyatomic called HSO4 -1. Now if that hydrogen had not been there, then it's SO4 -2. But the other word of calling this is called bisulfate. Okay, so HSO4 doesn't equal electrically neutral. So what happens is this 1 gets transferred over, but we don't write 1s. But this 2 comes over, and you cannot touch that 4, that subscript. On a polyatomic, if you change that subscript, it's not that polyatomic no more. You have a completely different polyatomic. So what you need is what's called the parentheses. So I got to bring that 2 over, but I need everything to get multiplied by 2. So I'm going to put this whole polyatomic in parentheses, and I'm going to put a 2 on the outside. So that 2 on the outside represents that everything in that parentheses is basically multiplied by 2. Aluminum is +3, and sulfate is SO4, -2. So I definitely need a crisscross, but I can't touch that 4. So I'm going to bring that 3 over here and bring that 2 over here. And because I can't touch the 4, I need some parentheses. So Al2, SO4, and then parentheses 3. And then sodium, Na+1. Now perchlorate is a polyatomic, ClO4, -1. Electrically neutral, so we put them together. Okay, and when you put them together, the charges balance out. Okay, they don't just magically disappear. Okay, sodium gained, sodium lost, perchlorate gained. They come together to make a compound, electrically neutral. And the last one, copper +2, and then you got iodite. So IO2 -1. Okay, can't touch a 2 on iodate, but I do need to bring that 2 over. So same thing, I need parentheses. So hopefully, ladies and gentlemen, this was helpful to you. And you know we're going to practice galore with this stuff. Okay, so I'll see you on the next one for molecular compounds.